Hey guys, it's me, Landon. I'll be your recitation host today, right back at my 6 o'clock time slot like I did the first 2 weeks. So today we are going to talk about MSTs, Kruskals, dynamic programming, and longest common subsequence, often abbreviated to LCS. So first thing we need to do for that is revisit some of the graph terminology we mentioned last week, and kind of go over some of the other concepts that are specifically related to minimum spanning trees. One of the concepts we'll talk about today. Also remember that thanks for doing exam 3. All your homework should all be in. Pay attention and stay posted for announcements about the final exam. We're thinking about considering having some options for you guys, and we want you guys to obviously stay engaged in the course. So look out for announcements and pay attention to those. Other things, if you have questions, the same Piazza format we've done before is still the same. Now your TAs are Anjana and Isaac. You can see their emails there, and if you want to post a question on Piazza, follow a similar format, put in the live recitation questions box, and then put in brackets the name of you want this answered in recitation or something similar. Besides that, I'm going to jump into beginning of recitation. So let's get started. Alrighty. Assuming someone will tell me if something isn't right. But yeah, we're going to go ahead and get started. So let's talk about graph terminology. So some of the other ones that are relatively important from last week is a subgraph is a graph G prime equals V prime comma E prime is a subgraph of G, V comma E, if V prime is a subset of V and E prime is a subset of E. So that just means if the subgraph is a thing, if the number of vertices is a subset of the actual number of vertices and the number of edges is a subset of the number of edges. Going forth with that, a connected graph is a graph in which each vertex can reach every other vertex. That means if I were to start at any one vertex, I'd be able to get to all the other vertexes using only the edges that currently exist in the graph. Contrastingly, disconnected graph is a graph in which any given vertex cannot reach all other vertices, right? So that also makes sense as well. Think about it if I was going through airports and I was stuck at the airport in Houston and didn't have a flight to get to Atlanta. And then from Atlanta, I could get up to everywhere else, get to New York City, San Francisco, Chicago. But I'm at Houston right now, so I can't currently get to every other vertex in the graph. There's no edge from Houston to Atlanta or Houston to any other edge in the graph for that matter. In that case, I would be dealing with a disconnected graph. A cycle is a pair of vertices that returns to initial vertex. So that could be something as simple as me having a flight from Atlanta to San Francisco and having a flight from San Francisco to Atlanta. Or it could be more than just two vertices involved. It could be a flight to New York, then a flight from New York to Chicago, a flight from Chicago to San Francisco, and then a flight from San Francisco back to Atlanta, right? As long as I can start at one vertex and then eventually get back to that same vertex, then that's considered a cycle. And we'll see that cycles come into play with the minimum spanning trees because we're not allowed to have any of them. Acyclic graphs, on the other hand, will contain no cycles. They will never contain a cycle, and that's an important property because minimum spanning trees have to be acyclical, right? There are also some properties of graphs and algorithms we can perform on acyclic graphs that you'll probably talk about in CS 3510 or one of the more advanced theory classes. Going from there, we talked about this before, a tree is really just a connected acyclic graph, right? The AVLs and stuff that you've been dealing with earlier in the course, they have a root where you can enter, and from the root, you can reach all other vertices in the graph. But from those leaves, I can't ever return back to the root. There's no edge that goes from a leaf node back to the root. Cool. And then a spanning tree is a subgraph that includes all vertices, is acyclic, and connected. Right. That's probably the most important term of today, right? So I'm going to circle over right now. It's this one right here, right? A subgraph that includes all vertices is acyclic and connected. I'm going to go ahead and go into presenter mode because, why not? Oops, where's slideshow? Right there. Play from current slide. Great feature. Cool. So spanning tree is a subgraph that includes all vertices is acyclic and connected, right? So it cannot have a cycle and it has to be connected. It has to span the entire, graph. And that's very, very important. If we ever have an unconnected graph or disconnected graph, we cannot have a spanning tree. And it says, note, we cannot connect an unconnected graph. Therefore, an unconnected graph does not have a spanning tree, right? It's also possible for a connected graph to have multiple valid spanning trees, right? There's not one unique spanning tree per graph. And we'll see in a second that there isn't necessarily one unique minimum spanning tree per graph. There can be multiple. So I'm going to head and dive into the right half of the slide and talk about minimum spanning trees. MST is the acronym that we associate with minimum spanning trees. MST, a spanning tree that has minimum weight, i.e. minimizes the total weight of the set of edges, right? So it's not good enough just to have a spanning tree. Sometimes we want to know, okay, what with the least cost, the least total weight, how can I get to, what are the edges that I can get to get to every single vertex in the graph? What are the edges that compose that? Right? And that'll be a minimum spanning tree. So it's a quote unquote stripped down. If you were seeing me in person, I'd be doing air quotes. It's a stripped down graph with air quotes again, unnecessary edges removed, as in kind of the heavier edges or edges that are connecting things that are already connected by cheaper edges, right? So those would kind of be the unnecessary edges we'd consider there. Unconnected graphs do not have an MST, just as they do not have a spanning tree, right? That makes sense. If the graph is not even connected, there's no possible way I can span it, no matter what combination of edges I use. Going forth, a graph may contain more than one MST if there are multiple sets of edges with same minimum weight. That's what I mentioned earlier. There's not necessarily a unique MST per graph. There will always be v minus 1 undirected edges or 2 times v minus 1 directed edges. If this was a real recitation, I would ask someone in the audience why 2 times the quantity v minus 1 instead of just v minus 1. And the answer for that is because of directed edges, right? If I have an edge going from A to B, in the representation that we usually have you guys do on your homework for an MST, in that case, we would input the edge from A to B as well as the edge from B to A, just because that's how we're representing edges in our graph, right? So if I'm adding both the forward edge and the reverse edge to my minimum spanning tree, I will add, then I will eventually have 2 times the quantity v minus 1 directed edges. However, if it's an undirected graph, then I'll only have v minus 1 undirected edges, right? That makes sense. I'm just multiplying v minus 1, the quantity v minus 1 by a factor of 2 to handle adding both the forward edge and the reverse edge. And it says recall, I already mentioned that. And then this is the terminating condition for your algorithm and a validity check for your algorithm. Note that it is not the only terminating condition. I'll talk about the other one in a little bit later here, but this is one. I mean, as soon as you've reached 2 times the quantity v minus 1 edges, I'm not going to go back and forth between v minus 1 and 2 times the quantity v minus 1 anymore. But if you reach that number, well, you're done. You've added all the edges necessary for a valid MST, and there's no reason to continue with your algorithm. The same way is kind of when we had in Dijkstra's, if I had visited every single vertex in the graph, well, I've already found the minimum path to every single vertex in the graph. There's no reason for me to continue. There's no reason for me to continue and consider edges in the graph from that point. Okay, so now that we got all that terminology done, I'm going to go to the next slide. So this is just basically just demonstrate kind of how many edges will be in this graph. So I have 1, 2, 3, 4, 5, 6, right? So v minus 1, I will have 1, 2, 3, 4, 5, right? And that makes sense. You can look at this for a little bit longer if you want to. Number of vertices I have is 6 minus 1, 5 undirected edges or 10 directed edges. That's just a little visualization for you, although we will use the visualization tool later, so that's cool. All right, I'm going to can the slideshow, and now we are going to go to the Viz tool. Oh, not the Viz tool. Never mind. We're going to go to the whiteboard. Wow, and that is extremely blurry. Let me see if I can do something about that. Cool. Is that better? Yes, a little bit. I'm going to move this a little bit closer because it seems like it's maybe a little bit hard to view from your guys' angle. Hopefully that doesn't smother some of the bottom of the screen. Oh, it's a little bit more readable. I'm going to move it back a touch, actually. Is that good? Yeah, that's good for now. Okay. All right. We're going to go through. So Kruskals, this is actually my favorite algorithm in the entire course. Right? Why is it my favorite algorithm in the entire course? Because I love the concept of a disjoint set, which we'll get to in just a little bit here. But Kruskals is one of the algorithms needed that can, once it's performed, produces a valid MST. If one can be found on a graph, if one can't be found on the graph, usually we return null or some kind of sentinel value to determine that an MST is not possible on that graph. But Kruskals is a greedy algo Nice, Landon, starting off strong. Oops, I'll go. That finds an MST of the graph, right? So it's a greedy algorithm that finds an MST of the graph. I don't want to delve too much into the definition of greedy because that's probably a topic that's better scoped for a class like 3510 or one of the other theory classes. But essentially, you can think of greedy in this scenario is that after I dump all the edges in the priority queue, which is one of my bullet points down here, once I do that, I'm dequeuing the cheapest edge every single time, right? And by doing that, that's considered kind of a greedy approach, right? I'm really kind of throwing all caution to the wind, saying, you know what, I don't care. I'm just going to keep on dequeuing the element with, or the minimum element for my priority queue. So that's kind of a greedy approach to finding minimum spanning tree. Notice that this is only possible with an undirected graph. And that kind of goes back to our definition of MST. If I have a directed graph, right, think about it, if I have a flight from Atlanta to Houston, well, then do I also have a flight back from Houston to Atlanta? There are a little bit of conflicts there. So we're only, when we think about MSTs in this course, we're going to think of them only being done upon an undirected graph. Right, so that goes back to our definition of MST that I mentioned earlier. Cool. So generally when we return an MST for a graph, we usually represent it just by a set of edges, not with order, but just a set, a dump. Here is the set of edges that construct this minimum spanning tree. The hash set, however, won't work. Right? We're using a hash set in a lot of our other algorithms, using it for the visited set in BFS, DFS, and Dijkstra's. And we would actually use it in Prims, another MST algorithm that you may have seen videos for or not, but we won't use it here, right? Which is cool. I actually like a disjoint set even more. I think it's even more unique, right? So you may be asking yourself, okay, he really likes disjoint set. Now what in the heck are they? So a disjoint set keeps track of separate groups of elements, right? Think of it as, you can think of it as if you had all the people at Georgia Tech, kind of each group would be separately, maybe a friend group might be a little clique or something like that. But notice how all the nodes in this case would be the students, right? But I want to keep track of separate clusters, right? Separate, maybe say student organizations, right? Which is the first student organization you got into at Georgia Tech. Notice how I want to quickly see, okay, am I, are these two people in the same first organization at Georgia Tech? And I want to be able to find that out very, very quickly. Not my best example I've come up with in half a second, but we'll get through it no matter what. So a disjoint set keeps track of separate groups of elements. Initially, though, each element starts out in its own set, right? So initially, when you initialize your disjoint set, each element starts in its own disjoint set. You think of it as a cluster of its own. And I've actually denoted that down here, right? So A is in a cluster of its own, as is B is a cluster of its own, C is a cluster of its own, so on and so forth, right? Cool. And there are only really two operations we're going to care about for disjoint sets in this course, and really probably overall. So two operations are important: find and union. Right? I denoted them right here. Cool. Find returns an ID for that group of elements, right? Basically, the point is that if I call find on any element in that cluster, I'm returned the same ID. I'm returned the same cluster ID. Think of that as, let's say the ID for that organization at Georgia Tech I mentioned before. Imagine each one had a unique ID, and that if I tried to get the organization ID for anyone who's in that organization, it would return the same number. So I could very, very quickly tell, I could compare those two IDs and say, okay, well, if they're the same, those two people are in the same organization. If they're separate, well, they're in separate organizations, right? That's kind of the point of the find, is it's an ID. The next is union. And union takes two parameters. I tried to denote that by having the first argument here and the second here. So it takes in two arguments, and it basically says, okay, now I want to union these two together, right? I want to merge these two sets together, right? And that's really, well, I guess one can't really be done without the other. Well, one is kind of useless without the other, but union will union two groups together. So that afterwards, if I were to call find on anything in the first, anything that was in the same disjoint set as the first argument, and anything that's in the disjoint set of the second argument, well, now they are all in one cluster together. And then if I were to call find on anything in that cluster, it would return the same ID now. I have merged those clusters together, right? Those friend groups have merged together. Cool. So I'm going to get into kind of a little example of kind of disjoint sets just to kind of show you how they work. And then I think, honestly, the easiest thing is we're going to be able to see is on the viz tool a little bit later. So let's talk about kind of how a couple operations would work with disjoint sets. So right now, I have a cluster for each of these, right? Now, if I were to call find on A, that would produce A. If I were to call find on B, that would produce B, so on and so forth. If I were to call it on E, it would produce E, F would produce F. Let's say I want to union these two together. If I were to union A and B together, and there's really no rhyme or reason to it, but it's not really important. It's beyond the scope of the course. is what I would do is I would map B to A, right? Notice how in a lot of other structures, a lot of other data structures we've seen before, so most of the time the pointers go from the root towards the leaves. Disjoint sets are actually the opposite. All the pointers go to the root, and we'll see why that's crucial in a second. Now, if I were to call find on B, it would produce A. Now, if I were to call find on A, it would produce A. So you may be saying, okay, well, why did the idea for B change? Well, one, because I union them together. But two is when I call find on B, what it basically does is it shoots up towards the root. And whatever is at the root, that's what it returns, right? So all it did was it started at B, it went to the root of A, returned that. Let me try and union C to B, right? So what happened is generally when you're unioning something, you union the root of one to the root of the other. So the root of C is C, the root of B is A. So then this would look like this, right? So now if I were to call find on B, it would be A, find of A is A, and find of C is also A, right? Let's say I want to do union E to F, right? Cool. So now if I were to call find of F, it would be E, find of E would also be E. Now let's say I want to union E and C. So what would that look like? Okay, well, what is the root of E? Conveniently, it's E. What is the root of C? It's A. So to do that, I would union this, I would point this all the way up here to A, right? And so now if I were to call find on F, it would return A. If I were to call find on E, it would return A. Find of C, also A. Find of B, A. Right? Everything now is in the same kind of cluster here, except for, D, which seems to be ostracized over here in the bottom left. But if I were to union D to, let's say, I don't know, F, it's still, I would merge D over here to A. So now we see that A is the root of all this tree, right? But instead of how in a binary search tree or a heap or something like that, where the pointers are going down towards the leaves, it's actually the opposite. The pointers are, this is a leaf right here. This is a leaf, 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 right? How is the initial root determined? We give a disjoint set after union the first two vertices. Which one becomes the overall root? Which will become the ID for the group, and how is it determined? So good question. I'm glad you asked that on Piazza. You can pick a convention. It doesn't really matter which one you use. As long as you're consistent, that's really all that matters. And the ID itself will probably be a hash, maybe of the memory location of A or the memory location of B or something like that. Don't worry as much about how the ID, as long as you can draw this tree, and if I were to union something to something else, you can draw that so that if I were to call find on F, it returns the same thing as I called find on A. That would be completely suffice in this course, right? It wouldn't be super important. How the idea is found and the convention of doing whether B to A or A to B isn't super important because eventually they're going to have the same ID no matter what. Just a matter of what that ID is, which could change from implementation to implementation. But great question. Thanks for asking that on Piazza. Cool. Okay, so I think I'm done with disjoint sets. Probably talked my tail off about them because I love them so much. Now I'm going to go into the actual kind of high-level algorithm of Kruskals. We're going to talk about that. How am I doing on time here? 6:19. Great. More on Kruskals. High level. We're going to add edges to the MST, minimum spanning tree, in sorted order based on priority queue. Right? This kind of goes back to the greedy approach I mentioned before, how I'm just taking the cheapest edge every single time and attempting to add that to my valid MST. However, I'm not going to add any edge to my MST if it were to cause a cycle. Right? Kruskals is different as compared to prims, where prims starts at a vertice. It starts at a vertice just like BFS, DFS, and Dijkstra's. Kruskals, however, doesn't have any starting vertex at all, right? And that's why it's interesting is that we can't use the visited set to detect cycles like we were doing before with prims, although you guys didn't learn it this semester. We have to use a disjoint set because we have to compartmentalize the different clusters of edges. And you'll see that better in the visualization tool in a second. Basically, we're going to skip any edge that will cause a cycle. This is done by using our good old friend find in our disjoint set. And we're going to stop as soon as the MST is found. I talked about that earlier, the terminate condition. So it's going to terminate once I have 2 times the quantity E minus 1 edges. It's assuming I'm adding both the forward and the reverse edge. Cool, so let's talk about the algorithm. The algorithm, we're going to initialize the disjoint set. And the disjoint set, basically as an argument to its constructor, usually takes the entirety of the set. Right. So in this case, the thing that we want to be the elements of our disjoint set are the individual elements of our disjoint set are the vertices themselves, not the edges. The vertices will be care about. The same way in the visited set, those were also vertices as well. So we're going to dump all the vertices into the disjoint set constructor. I didn't ever rewrite disjoint set into that constructor. And then we dump all the edges in the priority queue, right? That's kind of cool too. We just dump all them in. We don't have to say, okay, I'm only going to add neighboring ones in Kruskals. We dump everything in the disjoint set, everything in the priority queue. From there, we go until the MST has been found, and that goes back to this condition up here, or the priority queue is empty, right? That's kind of our other kind of fallback terminate condition. That would be in the case of a disconnected graph. In a disconnected graph, I wouldn't be able to ever reach that Houston airport. So I would end up, the priority queue would end up running dry before I get that perfect number of 2 times V, 2 times the quantity E minus 1 edges, right? That's very, very important. So those are 2 terminating conditions there. This is for in the case of I have a connected graph. This is in the case of me having an empty graph. Yeah. Also, the next thing I want to talk about is dequeuing an edge. So this is inside the algorithm. First thing I'm going to do is always dequeue an edge. Cool. And then from there, as long as adding this edge doesn't cause a cycle, we can tell that by calling find on U and find on V. If they return the same ID, they are in the same. If they are in the same cluster, and adding that edge would then cause a cycle. We'll see that later in a second in the viz tool. If they're not, if they're in separate clusters, i.e. find and U and V does not equal each other, in that case, we're going to add the edge to the MST, and then we're going to union U and V together, because now that we've added that edge to the MST, now U and V most certainly are in the same cluster, right? So as long as they're not in the same cluster before, then we're going to union them together, and then we're going to add that edge and the reverse edge, if we were adding the reverse edge as well, under that there, to the MST. After, we still need to check the validity of our MST, because the thing is that we don't know if this algorithm terminated, one, because a valid MST was found, i.e. the 2 times the quantity E minus 1 edges check, or it terminated because the priority queue was empty in the case of a disconnected graph. Well, in the case of a disconnected graph, I don't want to return back to the user a MST that really is an MST. So I need to do a validity check to see if this is a valid MST. You think, validity check, how the heck am I going to do that? Well, it's almost trivial, actually. It goes back to the same thing I've been spamming since the beginning of this recitation. As long as the MST has 2 times the quantity E minus 1 edges, so I'm counting both forward and reverse edges, then that will basically mean that I have a valid MST and I can return it back to the user. Otherwise, if I have any other number of edges, I'm left with a disconnected graph, and I would return null to the user. Maybe throw an exception depending on your implementation, something like that, right? After I check my validity of the MST, I'm done, right? So now I've gone over this high level, well, a little bit of pseudocode as well, talking about Kruskals, and now I'm going to go back into the viz tool and really show you kind of the nitty gritty of disjoint sets and how Kruskals works. I'm going to flip my iPad back to me so I can see Piazza questions. Okay, 1 second. I'm going to go back to the viz tool over here. Nice, let's go to Kruskals. I'll send something on Slack really quickly. Question. All right, all good. Okay, cool. So now we're going to get into, oh, I got on my face cam. What's up? Oh, of course, cool. Okay, I used to have a face cam over here, but I don't think it's going to make it for this recitation. Okay, anyways, let's keep going. So here's our graph. I'll leave you a second to copy it down if you want. But you can see right now is that all the edges have currently been dumped into the priority queue, right? You can see this A of 1 to B, right? This one right here, and then A to C, B to C like this. And notice how right now the heap hasn't heapified, right? So these are not in, this is not a valid min heap right now. Notice how as soon as I hit step forward, it's going to convert everything in the priority queue here to a valid priority queue by performing, yes, the build heap algorithm, the one we talked about a little bit earlier in the course. You now see how a lot of these concepts are building upon each other as we're kind of getting deeper into the class with these graph algorithms where a lot of data structures are coming into play at the same time. So I'm going to step forward. I'm going to fix this priority queue. Cool. Now I have my order property. Now I have the minimum thing and everything else. All good there. Notice how this is the disjoint set right now. How the IDs, notice how the IDs of A, B, C, D, E, F, G, and H are all different right now. They would be the same if they were in the same cluster. But the same thing is like if I were to call find on A, it would return to me 1. And that's kind of how we're going to go forth in this example is that if Whenever I call find, it's going to return to me whatever is the set ID for that vertex. All right, so let's start. Well, the first thing we're going to do is DQ an edge. DQ an edge, we're going to DQ FH. Cool, that edge right there. Love the viz tool. From there, I'm going to check, are F and H in the same cluster? Is F in the same cluster as H? No, 6 is not the same as 8. Hopefully it shows that. Yep, that's 6. F of H is 8. Those are not the same. So that means, and I can see that adding this edge will certainly not cause a cycle. Obviously, I won't because it's the first edge in the set. But I now have validated that by using the disjoint set. Cool. So I'm going to step forward. I've added that to the MST. You can see now it's denoted by blue. It's because it's in the MST. So now I go back. Rinse and repeat. I want to merge them together. Merge them together. So now I'm applying 8, 6. Cool. Now I'm DQing again. Notice how F and H now have the same ID. Now if I were to call find on H, it would give me 6, the same as if I were to call find on 6. Or find on F, it would also give me 6. Now we have the edge A1, AB1 right here. Okay, cool. What's going to happen from there? We're going to check, are A and B in the same cluster? They're not. 1 and 2 are different from each other. I'm going to step forward through that. 1 is different from 2. Not equal. Vertices are in different sets. I can add that edge to the MST. Right now it's becoming blue. Cool. I'm going to union these together so they're the same set together. So now their ID is just changed to be the same. Cool. Now I'm going to DQ from the priority queue because I haven't reached my terminating condition yet. The priority queue is certainly not empty, and I certainly haven't gotten the right number of edges for a valid MST. So I'm going to grab BG, cool, right here. The next cheapest edge. Notice I'm doing kind of a greedy approach. I'm always taking the cheapest thing that's left. From there, what's happening is I'm going to check, okay, are B and G in the same cluster? B1, G7, nope. I'm going to go a little bit faster now. B7, nope, not in the same. Cool, I can add BG to the same set. And now notice what's going to happen is that G is going to get the same ID as A and B up here. So now A, B, and G are all going to have the ID of 1, right? If I were to call find on either A, B, or G, they would all yield me 1. Cool, let's keep going. Now I'm going to DQ FG, nice, over here. F and G, what's going to happen there? I'm going to get F and G. Notice how F and G are in decent clusters, but 6 is not the same thing as 1. So adding this is going to be fine as well. Now notice that after I do this, bingo bongo, these two clusters are going to merge together. They're going to be the same thing now. Boom. And this also, this is just kind of how we're demonstrating these two clusters merging. H, which was in the same cluster as F, will now have the same ID as A, B, and G as well. Right, so now A, B, F, G, and H are all in the same cluster, right? We can see that because they're all connected right here. Notice if I were to try and add an edge like HG over here, oh, conveniently that was the next one, nice. So I'm just going to keep on going and roll with it. I'm going to DQ now again. I'm going to get GH. Now this is the first problem edge we're going to see. If I call find on G, find of G is 1. Find of H is also 1. Notice how if I were to add this red edge, well, this would clearly be a cycle right here, which is no bueno. I can't have a cycle. So since the IDs are the same, find of G is 1. Find of H is also 1. Since these both are the same, I know that they're in the same cluster, and so I discard this edge. I'm going to just completely discard it. Vertices in the same set, skip the edge. Exactly. Nice. Keep on going. D and F. You can see that D and F are not going to be in the same disjoint set. One is 1. The other one is 4. So that's fine. I can add these two together, and now I'm adding them. I'm going to union them together, so now D is also going to have a thing of 1. Still haven't reached my terminating condition, so I'm going to DQ again. This A5, AC5 is also fine. A and C have different IDs. Had to burp for a second. Both are the same, 1 and 3. Well, but they're not the same. 1 and 3 are different. That's fine. I can totally add this edge right here. Although I'm going to union them together. And now we can see that really the only edge that's possible for you to add at this point is E. Because E is the only thing with a different ID, right? Next, we're going to see right now with BC7. Well, BC7, both are going to have the same ID. That's not going to work. Cool. B is the same. C is the same. That's not great. They're in the same set. I'm going to skip the edge. DQ again, B and D. That's also going to be no bueno. Both are going to be 1. That's not good. So you can see here, adding BD would clearly cause a cycle because I get from D to B to G to F back to D again. I would cause a cycle, then it wouldn't be a valid MST. So I'm going to discard this edge as well. Cool. E10G. Let's see. E and G are going to be in different sets. Find of E is 5. Find of G is 1. That means I can totally add it to the MST. That's perfectly fine. and then I'm going to union these together. Cool. And now I would also, if I wanted to use this as a terminating check, if it was an easy way to do this, is I'm done with MST for print or for Kruskal's if all the vertices have the same ID, i.e. they're in the same cluster. But it's much easier to honestly just check the number of vertices that are in the MST against the number of vertices I know that I have to have a valid MST. So I have 1, 2, 3, 4, 5, 6, 7, and I have, let's count them up, 1, 2, 3, 4, 5, 6, 7, 8. Wow, what a miracle, right? So because of that, I actually don't even consider CG13 at all because I already have every single element I need. MST has the correct amount of edges, I'm done. So notice how I didn't even consider this last edge because I already hit the valid number of edges to yield a valid MST. Now I would check to see that the number of edges now I check to see that the number of edges in our current MST is the correct number of edges for an MST of this size, i.e. do that check again if it's V minus 1 or 2 times the quantity V minus 1 if I was adding both the reverse and the forward edge. Besides that, then I would, then there'd be no reason for me to, then I would feel free to return it and then I'd be done. Cool. Alrighty, cool. So now I've done that, I'm gonna go back over here and talk about the runtime of the algorithm. Let's talk about the runtime of the algorithm. Make sure something's okay with my chat really fast. Okay. All right, cool. So the complexity for Kruskal's. Complexity for Kruskal's is a bit of a doozy. It's probably the most difficult and challenging in the course. The good thing is though, is that really all you have to do for this course is to memorize what the complexity is. You don't have to know what it really comes from. I'll write down right now because there's really I would have never guessed this when I was a student. It's O of E log Z, right? Actually, E log E, right? Oh, let me check. Sure, I'm not sure you up. E log E. Oops, my bad. This is actually AE. This is kind of garbo, so I'm going to rewrite it. O of E log E. Sorry for that garbo writing. We used to teach it as E log V. My first couple semesters TAing, and most recently we changed it to E log E. So you may be wondering what this is coming from. The E log E is coming from dequeuing from the priority queue a bunch. And that's really the main complexity of this algorithm. Doing find and join are both O of 1 for any number that is really foreseeable before the heat death of the universe. There's a huge number file proof on it that I may reference later, or you can watch Jacob's description of it. He does a much better job of explaining it than I do. Basically, for any number that could happen before the heat death of the universe, find and union are going to be O of 1, right? So they're not really factored into the whole complexity because they're O of 1. However, adding everything to the priority queue initially is a cost of E. However, E log E is going to trump E, just the cost of E. E log E is going to trump E log E plus E, so we just leave it with E log E. If you want to go more in depth with why this is the case, you can watch Jacob's discussion of it. There probably isn't a great one on the module videos since we probably have changed it since then. Feel free to email me if you want to talk about it more. Really, the only thing you need to know, though, is that if we ask it on an exam, as long as you know that it's O of E log E, not V, O of E log E, then you're perfectly set. Cool, and that's really all I need to know. If you want to know more about it, I'm happy to talk about it. Just don't want to waste time on a recitation talking about it specifically right now because it's not super important it's a little beyond the scope of the course. Cool, why find? I really talked about that earlier. If they're in the same cluster, they're going to return the same thing, and adding that edge will cause a cycle. So I'm not going to touch on that anymore. I don't think I need to. Cool. Now let's go into dynamic programming, kind of the second topic for our recitation today. Cool, dynamic programming intro. Dynamic programming is a strategy for solving a subclass of problems that can be solved by breaking down small repetitive subproblems. By breaking down a big problem, a big problem into smaller subproblems, into small repetitive subproblems. We want them to overlap. That's actually the goal. So solving these subproblem results, we're going to solve these subproblem results and then save them so we can reuse them later when we're calculating kind of bigger subproblems. And you're saying this sounds super ambiguous. It does right now, honestly. until you see a couple more examples, and honestly, probably more examples than we're able to show you in this course. We really wanted to introduce you to the concept before you get into 3510 or some of the more advanced theory classes. If we counter, we're going to solve subproblem results to use later. If we encounter an already solved subproblem, we can reuse the result. And that's kind of the goal, is that if I find something that to arrive at the answer for some problem, I'm recalculating the same result over and over and over again, it may mean that dynamic programming is a technique for solving this problem that may be very, very effective. And it builds off the results of these smaller subproblems to use to solve larger subproblems. Kind of these smaller subproblems kind of build up on each other until eventually, by solving all the subproblems, you've actually solved the original problem to begin with. Still a little bit ambiguous, but we'll get there in a second. It's typically seen as storing the results of recursive calls, and it's sometimes called memoization or caching. And notice that this can have a huge effect on runtime. We'll see an example in a second of reducing an exponential runtime. Exponential runtime is terrible, right? It's really, really expensive to compute, to something that has its polynomial runtime. For example, I'm going to dive right into Fibonacci, and then I'm going to go back to kind of exponential runtimes. So when we're calculating the Fibonacci number, everybody knows the definition of a Fibonacci number is we start at 1, and we go to 1, 1, 2, 3, 5, 8, 13, etc. Right? And basically what happens is, to start it, I'll do an LF here in case no one's not familiar with it. Basically, I start with 1 and 1. To get the next Fibonacci number, I add these two Fibonacci numbers together to get this one. To get the next one, I do these two to get this one. So if I ever wanted to find out what is the nth Fibonacci number, right? Well, then I would have to go all the way back, right? Or so you would think. So that would kind of be the naive approach to trying to figure out how to calculate the Fibonacci number. All right, so usually what we do is, here's my little class that's drawn fairly scribbly because on my last couple of sheets of paper and can't really find a lot of resistance against the board. I don't know why I'm telling you that. But public int fib, so it has a parameter of n. That's the number that I care about at that point. So if n is equal to 0, I return 0. Else, if n equals 1, I return 1. Otherwise, so those are kind of the base cases for the algorithm. I guess 0, is also a Fibonacci number. Otherwise, I want to return the Fibonacci number of n minus 1 plus the Fibonacci number for n minus 2, right? So I want to calculate it for 3. Well, to find that, I need to find the Fibonacci number that is this. I need to add the Fibonacci number that's 1 less than this plus the Fibonacci number that's 2 less than this, right? So what that ends up looking like, for example, for 3, well, for 3, it's not even that cool, but let's say for something like 5, right? For 5, what happens is I start with 5, right? And this is going to be the tree of recursion that you're going to see. If I start with 5, well, to find that, I need to solve n minus 1 and n minus 2. If I solve n minus 1, well, that's fib of 3. So this is fib of 5. This is fib of 3, right? This is n minus 2, right? So from there, wait, did I mess this up? Oops, sorry, this is going to be 4. My bad. Then from here, what I'm actually going to find is then I have to find the fourth Fibonacci number. Well, I actually need to find, I need the same formula again, right? So I'm going to do a fib of 3, and, well, this is going to be fib 3 over here. Right, so this fib 4 and 3 are going to come from this first recursive call, n minus 1, i.e. 4, plus the second call, right, which is going to be fib 3. Same thing for fib 4, going down the recursive stack. It's going to be 4 minus 1 to get 3, and then 4 minus 2 to get fib of 2. Right, well, to get fib of 3, I have to keep on going downward. To get this, I'm going to get fib of 2 and fib of 1. Well, I'm still not done because I still have this case of 2. This over here, now going to be a fib of 1, right? And a fib of 0. Now, the good news is that these are actually base cases right here. So this is going to equal 0. This is going to equal 1. So I can find out that the Fibonacci number for 2, the third Fibonacci number is 1, right? But then fib 1 over here, I still need to, well, this is also a base case, so this gets evaluated to 1. That's cool. The thing is for fib 3, so I've done all this work just to calculate fib 3. But this fib 2 over here, I'm going to have to compute again. but that seems a little bit silly considering that I've already computed the result for fib of 2 over here. It is a little bit messy, I guess it's probably hard to see, but basically the idea behind dynamic programming is that I've already found the result for fib 2. There's no reason for me to recompute it again, right? So that's what we're going to talk about the topic of memoization a little bit later. For fib 2, I have to do the same thing. This is fib 1 and fib 0, right? And I'm saving room because I still have to do fib 3 over here on this side, right? So I've done all this work. I've done to find the fifth Fibonacci number just to get to 4. 1, 2, 3, 4, 5, 6, 7, 8 calls. Find the 4th one. You're ready to see what happens when I go over here to this one. We'll have to do the same thing. Fib of 2, fib of 1. This is fib of 1. Oops, this is a base case. But you can see I already did the work to calculate fib 3 earlier when I was calculating 4. So why would I have to recompute the answer to this problem? I'm going to go back up to my live recitation questions channel. Cool. And so you can see how basically to calculate a number, not only am I recursing once, I'm actually recursing, it's branching by a factor of 2 every single time. This is branching by 2, and then by this one, it's also branching by 2, branching by 2, 2, 2, 2. This is only to calculate the 5th Fibonacci number, right? So this is as a branching factor of 2. So this actually has a complexity of O of 2 to the n, right? O of 2 to the n because it's branching by 2 every single time. If I were to take this to, let's say, like the 3rd power, something like that, that would be 1, 2, 3, 4, 5, 6, 7, 8. I would have a ton of calls. This complexity is so bad to the point of on your computer, if you were to try and calculate, don't do this because I don't want to pay for your new computer, but if you were to calculate, like, let's say like the 70th Fibonacci number, your computer would actually run out of memory. It would actually run out of memory if you were to calculate just like the 70th Fibonacci number, right? Actually, a relatively small Fibonacci number in the big scheme of things. That's how bad an exponential runtime is. The good news is that we haven't lost all hope. There are better approaches. Let's go over here. We can tweak this just a little bit to use memoization. We can use a hash map, kind of butcher the writing of hash map right there, to see if we have already completed that case and avoiding that recursion. That was what I talked about when I said, well, I've already done the work to calculate fib 3, so why do I need to calculate it again? The thing is, I didn't know if I had calculated fib 3 or not already. There was no way of me for knowing that. But now we're going to use a hash map to store the results of fib 3. So if I ever need to use it again, all I have to do is just retrieve whatever was mapped to fib to 3, and I completely use that, and that's completely fine. Cool. So we can use a hash map to see if we've already completed that case, avoiding that recursion. So we have 2 cases. A, if we haven't computed that number yet, we compute, and then we store this result in the hash map. Our only other case is, well, now I check my hash map, and I actually have computed it before. Now I just return that value in the map, right? So now we kind of see something that looks something like this, right? And I should have initialized like my hash map up here or something like that. I'm not going to write that down because I'm limited on space. But now I have the same method signature, same 2 base cases. But if the memo contains, I'll write this over here. Memo is a, hash maps integer. Yeah, I'm doing the generics because I grade a lot of stuff with generics. Memo equals a new hash map, blah, blah. Some of my worst writing in history, but you have to deal with it. So memo is a hash map. It maps basically that Fibonacci number to its result, whatever I would have actually ended up calculating in all those recursive calls, right? So if that memo contains the key of n, if I've already found that result for fib 3, if I haven't already found the result for fib 3, I actually end up having to calculate. I don't really have an option. So I'm going to recurse the fib n minus 1 and n minus 2, right? However, though, it's more likely that I've calculated those subproblems before, and then I can reuse those to reconstruct result without having to go down all the way to the bottom. Then, really, it's really that simple. All I have to do is return memo.get on n. Right, so now I'll show you what it would look like for fib of 5. Right, so let's see, fib of 5. Right, fib of 5, we go to fib of 4. Fib of 3. I'm not doing the other end of the recursion, just see that in a second. Fib of 2. So for each of these, I wouldn't have seen it in my hash map because my hash map is actually empty right now. soon as I get to 1, I realize I'm in a base case, right? And this also is a base case right here. These get evaluated to 1 plus 0. So then the result of, when I call fib2, the result of fib n minus 1 plus fib of n minus 2 is 1. So that means that 2 ends up getting mapped to 1, right? Cool. You think, okay, well, that doesn't sound super cool. Now, this call is finished. This returns a 1. Now, fib of 3, fib minus 2 of that is fib of 1, which I already know it's 1. Cool. Now I can see fib of n minus 1 is 1, and fib of n minus 2 is 1 as well. So now computing them together, it's 1 plus 1. So now 3 maps to 2. Cool, right? Then I keep going, fib of 3, or fib of 4, right? Well, the other half of that is fib of 2, and you're about to see it's about to come into play in a big way. Fib of 3, I just calculated. I look it up in my hash map. It's 3, it maps to 2. So I know this immediately equals 2 without having to do anything else. And then fib of 2, well, normally I'd have to recurse again, but I check. Is it contained in my hash map? It is. So I don't even need to do any more recursion at this point. I always realize that 2 is mapped to 1. Right, so now 2 mapped to 1, boom, 4 is going to map to 3. Right now you can see that we're saving a little bit of recursion here. You'll actually see it in a big way in a second. Fib of 3. Remember how I had to go down all the way to the bottom of the leaves in the last one? Fib of 3, well, I check. Does that exist in my hash map, in my memo? This is memo right here. Yes, it actually does, right? It already exists, 3 maps to 2. So I don't have to do any more recursion. I already have the results of these problems. 3 plus 2, 5, right? 5 maps to 5. Now I'm at the very, very bottom right here. All I have to do is return memo.get of n, right? Return memo.get of n is 5, and I have my result. And way less recursion, right? And you can actually even do better than this. There's a way to even use like less recursive space. I'm not going to get into it today. You can look it up on your own. But basically, you can use a length n array, and then you can save a little bit more of. Actually, you can even do it better than that. You can even use just 2 pointers, because really the only two at any given time, the only 2 values you care about are the values for fib n minus 1, the values for fib n minus 2, right? So that's really, really cool. So now we can see that how by doing this, we actually transformed a 2 to the like an algorithm that's 2 to the n now is now is a polytime now is like a poly runtime, right? And so I want to see to make sure. Cool. All right, so now I'm going to go back into longest common subsequence. So longest common subsequence is the one kind of example that we use of dynamic programming in this course. Longest common subsequence is a problem where if you were not to use recursion, or we're not to use dynamic programming, the runtime would be extremely poor, excessively poor, to the point of I don't even know if it would be worth doing. I think it's an exponential runtime as well. Cool. So now let's get into what is this algorithm? So a subsequence is a subset of a string where each character appears in the order it appeared in the original string, but not necessarily in the same order, right? So for my name over here, Landon, right? LANDON would definitely be a subsequence. So would LAN. So would LNO, right? Because L and O are all characters in the string, and they also appear in the same order that they do in the word itself. Sorry, I lost focus for a second. Subsequences for Brown, our head TA, Adriana Brown, would be bro, right? BRO, bon, BON, similar to what I did over here. XYZ, or sorry, not XYZ. Brown, the entire word. The entire word is also a subsequence of itself. On, ON, also a subsequence, doesn't have to start with the first character. Those would all be valid subsequences for Brown. Not valid subsequences for Brown would be BOR, right? R comes before O, so it can't come after it in the subsequence. BNO, same reason, B, N, then O. The order's messed up. XYZ, none of the letters are even in the sequence to begin with. And then NWORB, it backwards, that is also not going to fly as well. right? I could also do something like B, R, Z. Well, B and R are both fine. Z is not, unfortunately. So this would be a no-no as well. Cool. So the LCS problem is that given I have a string X of length N and I have a string Y of length M, what is the longest subsequence in both? What is the longest subsequence these two strings have in common, right? And so you may be thinking, okay, well, I guess I could try every single subsequence of string X and see if it's actually in string Y. Well, doing that would actually be 2 to the n, exponential runtime again, which would be extremely poor. However, there's a better approach. The better approach is we're actually going to define a 2D array. And this is going to be kind of our memoization or our kind of caching of the problem so we can save results to use later on. Cool. So we're going to define a 2D array L to store the solutions to subproblems. The length of this is n plus 1 times n plus 1, right? So it's going to be n plus 1 long, n plus 1 wide. And we add a row and a column for 0. We have a 0 row and a 0 column, which I'll get to later. And so have a row and a column of 0. I just mentioned that. And basically, the value of L at I and j, right? I is pointing to string X, Y is pointing to string J, is if the characters of those, if the character of I of X, is the same as Y of J, as in, do I and J are they the same character? If they are the same character, we actually want to increase the running length of the longest subsequence, right? And it's really, really hard to, I don't have room, and unfortunately, this is actually like the last slide I have on this board. But it'll be better when we see it in the viz tool in a second. What's going to happen here is that if I and j are the same, then I want to take whatever the value was before I considered this letter in string x, and before I consider this letter in string y, right? So I minus 1, j minus 1, and add 1 to it. I want to increase the longest running subsequence of this of these two words, of these two strings. So I'm extending the subsequence in the case that they match each other. Well, what if they don't match each other? Probably the more likely case. If they don't match each other, well, then the longest common subsequence up until that point is actually the max between like it's either the max between one less character in X and the same character in Y, or the same character in X and one less character in J, right? And so we use the longest common subsequence up to this point, right? Because if I have a subsequence of 3 and I reach a character that doesn't equal each other, well, then in that case, the longest common subsequence still is 3, right? It doesn't ever go back to a lesser number, right? It can only increase. So the length of the LCS can be found at the very, very end at L of mn. Right? At the very, very bottom right corner, that's where you'll always find the LCS for both strings. And to reconstruct, we go backwards in a technique that I'll show you on the viz tool. But yeah, I'll skip over this line, which is a really important line. Subproblem, L of ij will store the length of the longest common subsequence from 0 to I and y 0 to j, right? And that's very, very important when I'm referencing it below. So I was saying that, okay, if the two characters equal each other, well, then I want to increment the longest common subsequence up to the point from 0 to I minus 1 and to the other string of j minus 1, right? And I want to increase the length of that running common subsequence. So not my best explanation of LCS, but I think it'll be much more insightful when you see the viz tool as well. So I'm going to go to that now. Cool. Let's go over to the viz tool. Hopefully you guys can still hear me. Cool. Okay, so let's go over here and do longest common subsequence. So this is the viz tool, super cool. Probably have plugged it already, but we keep doing it. So my two strings, S1 is Georgia Tech and S2 is Heritage, right? So this is literally the entire algorithm right here, right? It's literally that simple. So from here, notice how I have my row of zeros and my column of zeros. And that's basically just to help edge case the scenarios when I'm comparing these characters along this edge over here so I don't run into an index out of bounds exception. So the first thing I'm going to do is I'm going to check if H and G are going to be equal, right? I'm going to say H, are H and G equal? H and G clearly are not equal. So I'm going to take the maximum, i.e. the longest common subsequence, up to this point. So I'm either going to take the max above, and this is I j minus 1, and this is or I minus 1j, right? So what I'm going to do is I'm going to take the max of these two. They're both 0, so it doesn't really matter which one I pick. Then now I can see that, okay, well, if I'm just considering only G and only H, well, then the longest common subsequence between them is 0. They don't have anything in common, right? I'm doing the same thing. I'm going to go over here to E. Let's look at E. I'm going to say, okay, do H and E match? No, they don't. So the longest common subsequence would either be the longest common subsequence is whatever the longest subsequence was between H and G, or between GE and nothing, right? So 0 and 0, the max is still 0. Cool. Now I go over here to H, the same thing, and they're not going to equal, so I'm going to take the max of up and to the left. Cool. And then for R, same thing. I'm still going to be taking the max. So you're going to see that until I hit this H over here, every single value is going to be 8, or L is going to be 0, because I'm always going to be taking the max of 0 and 0, right? So this is going to be 0 as well. This is going to be 0. This is going to be 0. That's I'm going across the row entirely. Go to T. Nice. Go to E. Same, don't match. I pulled the max. C. They don't match either. Now I get to H. H, right? So now the longest common subsequence between H and Georgia Tech is the maximum longest common subsequence between no characters and Georgia TEC, right? That would be this index right here. So I'm going to take 1 plus that, right? Because the longest subsequence before this was actually 0. So boom, this goes to 1. Nice. We'll see this longer. We'll see this more as kind of the substring increases on the other axes. But G and E not going to equal each other, so it's going to pull the max of. Basically, what we're doing when we pull the max over here is I'm saying, okay, I want to take the max of either HE and nothing up here, that would be this cell, or I want to take the maximum of H and G, which is also 0, right? So that's going to be 0 as well. Cool. EE, match. So I'm going to take the longest common subsequence up to this point is going to be whatever the longest common subsequence was for H and G, i.e. this cell right here. I'm going to add on 1 of that. I'm going to add on 1 and go diagonally down. Right, so this is 0. So whatever's going to go in the bottom right box is going to be 1 plus that. 1. Nice. So over here to E and O. These don't equal each other. So that means that I need to take the max between up and to the left. But up and to the left means I'm either going to take the max between HE and GE, or H and GEO. H and GEO don't have anything in common. That's why this value is 0. But HE and GE actually have something in common. They have E in common. So I'm actually going to end up taking 1 as the max, right? The longest common subsequence between HE and GEO actually is 1. They both have this E in common. Cool. So I'm going to go again. This R doesn't match. I'm basically going to end up stringing this R all the way, or this 1 all the way along. 1 is going to get pulled from the left. 1 is going to get pulled from the left again. Pull from the left. Pull from the left again. They don't equal each other. Pull from the left again. Now I get to E right here. So I'm comparing this E and this E. They match each other, which is cool. So notice I'm going to be taking 1 plus whatever the diagonal is. The diagonal would be if I'm taking H with the pattern of Georgette, right? I'm not going to be tacking on this 1 over here because there aren't the longest common subsequence. There's only 1 E here. So I can't like double count the E over here and take this 1 and then add 2. I'm taking the longest common subsequence before I consider either of these two characters and then tacking on a 1 to that. I'm going to step forward, pull a 1 or pull a 0 from that one, add 1 of that. That's cool. 1. This is going to get 1 pulled over from there, 1 pulled over from there. I'm taking the max of either of these. Doesn't really matter which one because they're both 1. Cool. I go over here to R. R and G don't match. I'm going to pull a 0. R and E don't match, but I'm going to pull a 1 because they both have one. They both have one character in common. Nice. O matches. R is also going to match GEOR and HER. Well, notice that now I'm going to take the longest common subsequence plus 1 of HE and GEO, which is 1 because they both had E in common. So this is actually going to be 1 plus the diagonal. 1 plus 1 is 2. Nice. From there, going to G. Nothing's going to happen. I'm going to string along this 2 for a while. I think until the very, very end. Yep. Nothing else matches with R. So I'm just going to keep on pulling this 2 all the way along, right? So I can see that if I were only considering HER and Georgia Tech, the longest common subsequence would actually be 2. It would be from this E and this E, and this R and this R. And we can see this as we go later on, is that basically we're building up from these subproblems until eventually I've considered all of this string and all of this string, and that answer is going to actually lie in this cell down here. So I'm going to keep on going, step forward, GI, not going to match, so I'm going to pick 0. Not going to match, but I pick 1 because HERI and GE both have one letter in common. 1 is going to get pulled again. 1, 2 is going to get pulled again because GEOR and HERI. I'm going to get to be able to pull HER and GEOR. That's this cell right here. I'm going to get to be able to string a 2 along. Right over here, this is a match. Nice. I'm going to get to I. I and I match. I'm going to take whatever the longest common subsequence was for HER and GEORG. Right? GEORG was ER, 2, right? So 2 plus 1, I'm taking advantage of that diagonal. 2 plus 1 is going to be equal to 3. So my longest common subsequence up to here, Hgri and GEORG, is actually 3. ER and I is the 3 from this one, and ERI from HERI are part of this subsequence. I'm going to keep on stringing this along because there's not going to be any other matches. You're probably getting a little bit bored. Move a little bit faster. Right? Keep on stringing that 3 along. T and G not going to match. I'm going to pull a 0 down. Not going to match again. I'm going to pull a 1 down. 1. I'm going to pull a 2 down because it's the max, right? HERI and GEOR. I want to take this 2 from this cell right here. Cool. This is also going to get plugged down. Up into here, they don't match again. But I still want to take advantage of, I already have ERI and ERI. So I still have a longest common subsequence of 3, even though it doesn't end with either of these two characters. That's still fine. They still do have a longest common subsequence of 3. Cool. So I keep on going. Pull the 3 down. This gets 3 is here. When I get to T, T's match, so I get to use the diagonal. I'm going to add 1 of that diagonal, so it's going to be Georgia and HERI. The biggest match between them was 3 between ERI and this ERI. Add 1 of that because now I get to include this T and this T. And I get 4 over here in the diagonal. String this along, 4 and 4 and 4. Nice. From then on, GE, I'm going to go a little bit faster. I'm not doing anything here until I get to the A. Right? Over here, these A's which match each other. Now I want to add 1 to Georgie and HERIT, right? So I'm going to add 1 of that, 3. So this is actually going to be 4. Nice. Cool. Now these don't match each other. That's fine. I have a longest common subsequence here and a longest common subsequence here. Notice how they're all from the same characters. This 4 is from ERIA, but this one is actually from ERIT and ERIT, right? ERIT and ERIT. So they have 4 from different subsequence. That doesn't really matter though. I'm still going to take 4 because that's the max of either of them. I'm going to string this all the way along. Boom, nothing interesting is going to happen here. Nice. G, I'm going to get a match here finally, right, on the first one. So I'm going to pull along the 0. And this is why we have the column of 0. So I don't end up having like an index out of bounds exception on this 0 index array right here. Cool. The 0, 1, pull it over. This is going to get dragged all the way over. No other matches. Well, until a second here. 2, Heritag and George. I want to take 1 plus whatever Herita and GEOR. That's going to be a 3. I'm going to pull from the diagonal. Every single time I get a match, I pull from the diagonal right here. Add 1 of that. I'm even going along. I'm going to drag the 3 and 4s all the way over. Nice. Almost done, I promise, guys. I know this is getting repetitive. GE, no match. I'm going to pull a 1 down because at least G and G have a match of 1. We get to include that. Nice. GE, E. Well, GE and Heritage have a, they match this character, and they get to add 1 onto whatever the match was before, right? So I get to have 2 now. This is going to be pulled over from the 2, 2, pulling over 3, 3, 4, 4. Something interesting is about to happen. EEs match up. So now Heritage and Georgiate, right? So I want to add 1 to the longest common subsequence between Georgiate and Heritag, right? So Georgiate would be GE or E R E, or it'd probably be easier this way. ERIT. ERIT, that's 4. Now I can tack on this E over here. 4 plus 1 is going to be 5. Nice. I'm going to drag that 5 all the way along because there's no other matches. And boom, we're done. Now 5 is in the bottom right corner. That means the longest common subsequence has to be 5. However, if we wanted to reconstruct what the subsequence actually was, now I actually have to reconstruct and find it using another tool, like the last part of the algorithm. Basically, what I need to do is think about each of these being in their own little block. Nice. I'm glad the Viz tool has it. So now I can see that these are all 5s, these are all 4s, 3s, 2s, 1s, and 0s up here. So to find the longest common subsequence, I have two choices. I can either go up until I hit a boundary. When I hit a boundary, I mean I can't go up anymore because I'll hit a 4. I want to stay in block of 5. So I either go up as long as I can and then left until I hit a number that isn't 5, or I go all the way to the left and then up, right? Either convention will give you a valid LCS as long as you continue that convention throughout the entire process, but they might give you different LCSs. As we could see earlier, there are different LCSs, both of length 5, I think, in this one, right? Cool. So I'm going to go to the left over here. Boom. This one's going left first, right? And then now from here, I'm going to break diagonally up to the left and right. And whatever this character is, the one we leapt and went diagonal, that's going to be a character in our longest common subsequence. So the first one is E. We can see that that's denoted right over here in longest common subsequence. I'm going to go again. I'm going to go up as long as I can and then go left. I can't go left anymore because I did a 3. So now T is also going to become a part of our MST as well. Notice how I'm prepending each character on because I'm reconstructing it from the back all the way up to the front, right? That's another important thing. When you're reconstructing, make sure you reconstruct from the back to the front. So you're prepending characters instead of appending characters to the back. That wouldn't make much sense. ET is not the right order. Well, we'll see later on a larger version of the string that is in the right order. 3, I've hit a boundary up here. I'm going to go to the left as long as I can. 3, I'm going to add I to my longest common subsequence, prepend that. Boom. R is also going to be 1. Now I've hit the block of 1s. I'm going to go up. Can't go up anymore. I'm going to go to the left. Now I'm in this hole. Cool. I'm going to add E over here. And now E right is going to be, now once I hit a 0, I'm done. E right is going to be a valid subsequence of Georgia Tech and Heritage, and is also the longest common subsequence, or one of the longest common subsequences, all of length 5 for these two. I know that was a lot, but really there's not a whole lot to this algorithm. You just basically, at every single point, you say, okay, are they equal? If they are equal, I pull 1 from the diagonal. If they're not equal, I'm going to take the max of either up or to the left. Whatever this value is over here is the max length of the subsequence, and then you can visually kind of reconstruct them on the way back. Just make sure you hold the same convention, either going all the way up and then left, or all the way left and then up, right? Just make sure you hold that convention throughout the entire reconstruction process, or you may land with something funky as your longest common subsequence. Okay, cool. I'm going to go back to the whiteboard, and we're going to finish up this recitation, even a little bit early today. Actually, I'm going to get some water first because I'm pretty parched after talking for an hour and 10 minutes. Wow. Awesome. So really the last thing we have to do to talk about longest common subsequence is what is its complexity. You're thinking to yourself, okay, the easiest way to think about it is, what size array am I generating? Well, excluding constants, I'm doing an m plus n times m array, right? And so for every single character, we saw that in that grid, for every single character in n, I have to consider all the characters of n, right? And the next one I consider n all the way again. So for each character in n, I'm considering all m characters eventually in n. So that'd be m work for each character of m. Well, what do we think that's going to be? Oops, almost fell down. Of n times m. Boom. And that's our complexity, right? We can see that as if I had any sort of room over here. I'll try and do it like does and b. Right? For B, I'm going to consider B, then BU, then BUZ, then BUZZ. For E, I'm going to consider BE with B, BE with BU, BE with BUZ, BE with BUZZ. Right? So for each one, I'm doing M work, M, N. Well, how many times am I doing that? I'm doing that approximately n times. That's where I get m times n. Right? That's the complexity right over there. So I'm actually going to go back to my little desk and my little hidey hole, and I'm going to sit and wait for questions for a second. If you guys have any, awesome, feel free to answer them. I'll probably stick around for a couple minutes because I have a little bit of time. Let me see if there's any trivia on my sheets about LCS, if there's anything super cool about it. Multiple LCSs can be found. We'll talk about that. Fun fact, you can ruin a license plate game with LCS. Don't know what that's about, but that was in my recitation notes. Feel free to ask me guys questions on Piazza. I'll stick around for a couple of minutes. If not, I'll probably turn my computer, well, stop streaming and then turn my computer off in a little bit. But we only have one more week of recitations. The worksheet links will be in Canvas file under Files, Recitation Worksheets. If you want a more complex example of the Kruskal's proof of complexity, go to Jacob's video. He probably does a much better job of explaining it than I do. Although really all you need to know is that it's O of E log E. That's all you need to know. If you are curious, feel free to email me or Jacob or watch Jacob's explanation on it. If you're looking for more of an in-depth explanation on it. I'm gonna stick around for, I don't know, maybe a couple more minutes. Why not? Let me see if I have any more notes on Kruskals. Yeah. The first E log E part comes from doing a maximum of E DQs, and each DQ can take log E time because there's E things in the priority queue. An important note, though, is in the worst case, E is actually V squared, right? Because in a worst case, the number I have as the maximum amount of edges I can have is V squared, right? That would be each vertice has an edge to every single other vertice in the rest of the map. And that's true for all vertices, right? So V squared is actually the upper bound for E. But since it's O log V squared, since it's a log, we can drop the power out to the front to get O of 2 times log V. Since it's big O, we drop the O, and we drop constants to get O of log V. So now we're left with E plus E log V, which we can write as E log V plus 1. Then obviously the lower order term of 1 gets dropped in that sum to get our final result of E log V. That was true. That was the complexity we gave in the kind of a couple semesters ago. Now what we're doing is E log E is the most important thing. So as long as you know that, you can regurgitate that on an exam, that would be good enough. So I'm not getting very many more questions. I'm wearing a hat today because I can't get a haircut and my hair is officially too long to be socially acceptable on one of these things. But besides that, thanks for showing up. I don't know how many people